AI is a powerful tool.
This summit can help ensure that artificial intelligence charts a course that benefits humanity and bolsters our shared values.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Welcome to today's AI for Manufacturing webinar. My name is Lihui Wang, a professor at KTH, Royal Institute of Technology in Stockholm, Sweden. I'm honored to moderate this webinar. The topic of today's keynote is AI and digital twin use cases driving sustainable manufacturing. We are fortunate to have Mr. Malur Narayan with us today. Mr. Narayan is a proven technology business leader with over 2 decades of experience in technology industry, having worked in 5 continents and presently leads the sustainability GTM for Tata Consultancy services across North America. He brings an effective combination of corporate and entrepreneurial experience, having held a broad range of senior management roles at Notel and Tata, covering product engineering, sales, business development, and product management. As a co-founder and advisor to a few tech startups, Malur excel in helping companies in building their technology, creating across to B2B market and segments, along with a strong ability to connect at the C-level and to develop long-term business partnership. Malur holds a degree in computer engineering, a master's in computer science from Western University, Canada, an MBA from Tata Business School, Canada, and an advanced management program through Harvard. Malur pioneered a self-managed team in software development in the early 90s. His research in reverse engineering, inverse resolution, and induction led to the development of adaptive learning algorithm in machine learning. He has been speaker on international business for executive MBA program at Cornell University, Imperial College London, and Queen's University in Canada. Ladies and gentlemen, Without further ado, please join me in welcoming Mr. Narayan to the virtual platform. Please.
Thank you, Professor Wong. Today we're going to be talking about AI and digital twins and how it manifests itself in terms of helping drive sustainable manufacturing. I wanted to start, first of all, thank you for the introduction, Professor Wong. I wanted to very quickly set some stage here. In the early 90s, I was involved in some pretty groundbreaking work in reinforcement learning algorithms, what we call adaptive set training algorithm that was developed as part of my research. And that led to a number of different things that eventually, were both in terms of practical applications, also led to my interest in using AI and related technologies in the fields of both telecom, networking, semiconductors, and a wide variety of other industries that I've been involved in. And my current role is I lead emerging technology and sustainability in North America. If you look at the macro climate.
Sorry, Malur, are you meant to be sharing your screen?
Oh, am I not sharing my screen?
No.
Oops, sorry.
That's okay.
I thought I already was. All right, let's try this again. Is that better?
Perfect, thank you.
Right. So the macro climate in terms of where the industries are headed, particularly from a manufacturing perspective, is that there is varying forces. If you've heard of VUCA, where there's volatility in terms of the economies, significant amount of uncertainty with, especially with the pandemic. Complexities are continuing to increase because of the in every industry there's multiple suppliers, multiple technologies, and multiple data streams, all leading to significant complexity, and of course all of that leading to an overall ambiguous situation. That combined with a combination of, up until now, a lot of the focus was on financial compliance. But over the last decade or so, there's been greater and greater importance on the environmental, social, and governance components from a manufacturing perspective. All of that in spate, continuing to drive a current climate where there's significant inflation, supply chain challenges driving, and continued labor shortage, especially skilled labor, and greater and greater scrutiny on financial regulation and compliance, which means companies have to develop and build products with all of these issues in play, while still being able to increase productivity, being able to make sure there's 24/7 availability, as well as improved quality. And that is the macro climate that companies are operating in. And I wanted to set the stage there because that drives how technologies play a big role in alleviating this and meeting some of the challenges that we discussed here. Digital twins, as many of you may be aware, are essentially virtual replicas of physical assets that are in tandem or in step with their physical assets. So unlike a simulation where it's a one-off thing, or the digital twins specifically take into account significant amounts of data and combine a plethora of technologies, which I'll get into in a little bit. And what makes it even more effective is the ability to use AI in various aspects of the digital twin, both in terms of building the digital twin, as well as in terms of how you use it and how you apply it to various production scenarios. And when you take take into account the sustainability requirement, that digital twins could play a significant role in determining your carbon emissions, how you reduce your carbon emissions, how you plan better, how you improve your energy efficiency, how you reduce waste, and how in general you plan for a more circular production, circular DNA. This is a sort of a illustration of how a digital twin works. You have the physical asset, and you have the digital twin, which is in tandem. And the big difference is that it's in step. It's, if you think of them like two state machines, they're effectively in step because they have the same characteristics in term on the as far as the real-time data that drives it, using sensors, and then including all its long-term history of what are the states it's been in, different maintenance data, its operational history, as well as the big differences really around the ability to have statistical models and machine learning models that drive its prediction of different states that it could possibly go to, and that will drive greater benefits downstream. In terms of the technologies that are used in digital twins, there are really four categories. Largely, even though a lot of these technologies existed in some form or the other, even back in the 90s, really coming together of cloud, which drives compute and storage, AI, the advances in AI in terms of algorithms, as well as the ability to drive process large volumes of data, the advancements in IoT, particularly from a sensor technology point of view, and the commoditization of those sensors, and the more recent advances in AR and VR and visualization techniques. All of those effectively combine to make digital twins more viable now more than they were maybe 10, 15 years ago when the term was originally coined. And typically they've been used for very complex applications, very high budget applications, but more and more we're seeing very critical use cases even within production and manufacturing in very specific areas, without necessarily having to do a digital twin of the entire production system, or what we call a virtual factory. In terms of the approach and considerations, I talked about the four technologies in play, but really, the technology element is one part of it, but a lot of it comes down to automation, because if you want to improve the process, it really comes down to how you review, analyze, and how you make sure that the data is acted upon immediately. And while it's the deployment of sensors and the ability to use sensors is relatively simple, or is a manual task, but still doable as a one-time thing. The harder part is really being able to ensure that the relevant data is used and the analytics are automated and the decision making are triggered. The decisions are triggered automatically, and action is taken to reflect any improvements in the process. So a great example is in the agriculture environment, where you have apple orchards and you need, there's requirements for different types of needs of the water for the orchards, and the system should be able to trigger action and stop depending on not just the weather and environmental conditions, but also the soil condition, the nature of each individual tree. And that really, the more personalized and more specific your actions are, the more you're able to reduce your wastage and improve your resource usage, be it water or energy. And then the other approach we typically use is what we call in logistics, optimize information logistics systems, because it's not just about production, but it's also about post-production and how you make sure that the data doesn't get stuck anywhere in any one part of the process that prevents the next part of the process to take action. Some of the applications where we have seen a significant uptake is really, there's two elements. There's the building of it, and then there's the maintenance part of it. So predictive maintenance is a very clear use case of AI and digital twin. Optimization of production processes, be it one element of it or end-to-end. Optimization of supply chain, especially when you consider redundancy and multiple sources, and especially given that there's a huge push for Scope 3 reporting, more and more consolidation of suppliers, as well as making sure that you have alternate sources of supply are very, very critical. And then energy optimization and environmental impact analysis, as well as life cycle assessments. All of those are areas where we've been able to use AI in order to be able to drive greater sustainability objectives. In terms of the use cases, I mentioned before, there are really, you have the physical environment and the virtual environment and the digital twin. And then you have a variety of techniques as far as our AI is concerned, be it supervised learning, unsupervised, as well as reinforcement. All three categories are used. In the case of the two elements are really around the manufacturing itself, and then the health and maintenance of the production process. Variety of different applications, whether process control, optimization, process planning, design, the fault detection, optimization of schedulers and model designs, as well as the assembly line and logistics. I talked about that a little bit. On the maintenance side, it's really more, how do you use AI and digital twin for calibration so that your systems are running, your machines and systems are running at peak performance, detection of degradation and over time to make sure that you're replacing those parts or products as required. So those are some critical. What we find on the, there are use cases specifically for supervised learning where there's an extensive use of labeling, but it's also super time and labor intensive. And then on the unsupervised learning, the clustering helps with determining how you drive better heuristics for some of these processes. This is a sample reference architecture for a digital twin across a spectrum of different tools and methodologies. On the left-hand side, you see all the services and applications, the data processing, storage, compute power, etc. And then the middle is where you have a variety of all the things that are used, from sensors to actuators, IoT, the IoT devices, and then the structured and unstructured data that you use for modeling the various scenarios, and then the ability to use a variety of different AI tools as well as methodologies to be able to drive, depending on whether you're looking at prediction or classification or maintenance. And of course, augmented by some of the communication technologies that drive greater connectivity between those devices. One of the things that we've been doing at research within TCS in particular is we've been combining the use of a variety of these types of tools and technologies to create a digital platform, something called TCS Premap, which essentially enables the, one application is the integration of design of materials, manufacturing processes, and products. Because independently, you can't look at those three things as independent items. You really need to, in order to be able to get maximum benefit and optimization, you need to look at what types of materials best suit a particular manufacturing process, and what sort of types of manufacturing process best suit a particular type of product. And that's why we leverage, even before a design is built out, physics-based simulations, AI-based reasoning, a variety of different knowledge engineering platforms and reverse engineering systems that enable us to analyze processes in a much more intricate way. So you can see, things like process modeling and simulation, data modeling, and modular platforms. But all of that creates this. We have this thing called TCS Premap, where we can emulate and simulate a variety of different scenarios, even before you start thinking about how the production process evolves. Some of the use cases that we've built out with the use of Premap, as well as outside of it, are things, digital twin of factory. I'll talk about some of these here. Digital twin of skin, materials design. We've even done something for food, and then a couple of healthcare related examples, and then some smart city examples as well. In terms of the, in the manufacturing industry, there are really two categories here. I talked about this earlier as well, right? There's on the whole, the real-time element of it, which is during the production process, the before and during the production process. And then on the post-production, really more looking at preventative diagnostics. Some of the examples here, this is a example with the Japanese, large Japanese manufacturer that is using coal-fired power plants. One of the challenges there is the impurities that drive coal. The impurities of the raw materials drive a significant amount of wastage downstream in the process. So one of the things we were able to do is, using digital twin, be able to model how we can reduce the amount of, using sensors, be able to reduce the amount of impurities, and at the same time model that to reduce the overall, improve the overall production by almost 30%, quality by 30%, and not have to, and reduce the wastage by about 35%. A few in the steel industry, like the cracking, and then we've also have examples in the heavy machinery or on gas turbines, where we've been able to use things like anomaly detection and diagnosis using a digital twin for the process. In the steel industry, again, blast furnace there's sinter that is created from iron ores, and there's I have a slide here that talks about how we use the digital twin process to enable a more efficient process there and reduce wastage. A few more examples here, in terms of power plants with the ability to detect failure and reduce the flue gas desulfurization. And let me get right into a couple of examples. This is the digital twin of skin, which we created for a particular healthcare, a pharmaceutical company. In this case, you'll see, we were able to emulate what the human skin looks like and be able to model a variety of different testing that otherwise would not have been possible without So this, of course, prevents animal and human testing, reduces the need for that. And it's driven by a combination of both sensors as well as the physical replica of something like a skin to be able to emulate that in the virtual world. Sorry, 1 second. In the food industry, we've had use cases where we've been able to create something like a digital nose, as well as using the power of cameras to be able to reduce wastage significantly. So the one of the big challenges with food is that the condition of the item is not just you can't just look at it visually. You also have to look at the smells and a few other things. So this is something we've been able to do through sensors, and at least in a lab in a POC that we created, we're able to determine food quality based on a combination of both visual as well as sensory tools. We have also used digital twins to be able to create more in an enterprise environment, to be able to simulate a variety of different processes, whether it's end-to-end enterprise processes like whether it's HR, finance, shared services, as well as individual production units, etc., and to be able to move things around and play with it, and say whether you can have using a variety of different modeling techniques to be able to say, if you take something out, or if you remove a particular element, how it would expand, or if there was a black swan event, how that would impact your enterprise decision making. This is the example I was talking about with the steel sinter plant, where you have sinter, which comes from iron ore, also is a big polluter in terms of dust particles. So that is something that can be reduced dramatically through modeling and ensuring that the mix, your feedstock that's coming into the system is filtered and is pure, and also at the same time the mix of those inputs are orchestrated in such a way that it provides the optimum amount of granularization, as well as moving in, creating a sinter model that has the least amount of wastage. So that was done using a variety of MLDL models for improving the process itself, and also reducing the amount of deposits, etc. I mean, we have one of the things that's different about the way we've implemented this is that unlike in a typical scenario, you have a problem, you have the data, and then you have the model and the insights, and then you have a feedback loop. Here with the reinforcement learning agent that we have, we were really able to create more with the digital twin. We've been able to have the feedback loop within a sub process, instead of having to wait the whole process, and more of a bottoms-up approach to be able to optimize at every stage of the process, instead of waiting for the whole thing. And that really helps in driving more point solutions. So that's pretty much the core presentation. Some of the key takeaways. While the technologies exist, really it's about how you automate and bring those multiple technologies together to use digital twin and AI or machine learning for very pointed, targeted tasks. not everything applies to every situation. So, one of the biggest challenges is trying to figure out what types of technique, what types of tools, and what types of processes to use for different manufacturing stages and processes. CPG is a great example of that. And then the ability to do sustainable impact analysis both before and after really help in driving your overall planning and design for circularity. So that's my core presentation. I guess we can go with Q&A.
Thank you very much. And so today, Malur presented a very interesting presentation with lots of thoughts, and especially through different use cases in industry. I think this is a good starting point for people to ask questions. There's already one question came in from the audience. Do we have data on how effective these systems are in practice?
Yeah, we do. We've done some analysis for all of those examples that I showed you. We have data post and pre and post. We've written case studies. I'm happy to share that with you post this. We've seen improvements of anywhere from in some cases 15 to 20% improvement in reduction of waste. We've seen improvements up to 30 to 40% in especially on the predictive maintenance side, where you're able to reduce costs substantially by being more preemptive as opposed to after the fact.
Yeah, these days DT is really popular. Many people use digital twin for a different purpose. It also creates some confusions. What type of DT can we use? Or sometimes if people even have a confusion how to draw a line between conventional simulation versus digital twin. Do you have
I think I read yesterday
characterize that this should be digital twin, not a conventional simulation software?
I think it comes down to your specific application, right? Obviously, it has a few factors you have to consider. Cost is a big factor because creating a DT is not trivial. It requires significant amount of both expertise, and a variety of different expertise, as well as hardware and software that you need to build specifically for that. Even though there are many available tools, you still need to customize it for whatever application you're building it out to. So it's a significant cost. So you have to look at the downstream benefit of that versus doing a more plain Jane simulation. I think yesterday I was reading that BMW just is implementing its DT across all of its factories in Germany. So that was something that I thought was, it's becoming more and more mainstream, where you're able to, especially because there's so many challenges that I talked about in the macro environment, particularly from a supply chain point of view, and also from a demand point of view. It makes it more and more critical that if you're able to implement it across the value chain end to end, it has much greater benefits, both from a cost and perspective, and also from a value and quality perspective, also from a sustainability point of view.
Okay, now we have another question from the audience. If you can share, do you have any figure related to the ROI of a digital twin?
Yeah, we have in the case of the application where we had we've used. We've not had a lot of POCs that we've done. In terms of real applications, the two that I talked about, one was in the steel plant. We were able to, I don't know how you characterize ROI, but the ability to be able to predict various scenarios is both tangible and intangible benefits. The tangible benefit, of course, was there was a 28%, 29% reduction in overall cost of the production itself, and there was over a 40% reduction in the number of trouble tickets and number of support requests that came, or even the number of defects was reduced over 42%. So those are all tangible benefits. The intangible ones are more around productivity, wastage of time, wastage of resources. So those I can share a couple of POCs examples there on our website. I'm happy to share with the.
Thank you. DT can be applied to different domain, and sometimes the application may be more real-time driven or have a real-time constraint. Sometimes it's more you can take time, like an offline simulation, but it's in a digital twin environment, satisfies the characteristic. If we apply digital twin to real-time applications, this is a true challenge to me, because on one hand, we need to collect the data. It takes the time, and sending it to the digital twin to do the analytical process to make a decision, and eventually need to send it back to the controller or to the physical twin to make it work. So this real-time constraint for company, how do they satisfy this requirement if it's in real-time application? Do you have any insight solutions to address the problem?
Yeah, so I think you're absolutely right on the money there, Professor Wong. The I think what differentiates DTs in most cases is the real-time nature of being able to simulate a virtual asset that is exactly in step with the physical asset. I think what we've seen in with the advent of networking technologies, with the advent of cloud, with the advent of sensors being relatively commoditized, we're seeing the opportunity to deploy more and more real-time data and sensors. While it's not just so at least the economics of it are becoming far more affordable. As far as latency is concerned, in real-time situations where it's mission critical, obviously you need to have 5G or advanced even wired networks to be able to provide real-time communication between the sensors, the controllers, and the physical asset and the virtual asset. That is we're seeing that more and more companies are adopting that with the advent of 5G. There is definitely significant adoption. The adoption rates are significantly increasing over compared to, say, 3 or 4 years ago.
Yeah, obviously enabling technology become more and more accessible to a company, to general public. I guess this digital twin technology will be more mature, will become part of the daily life.
One good thing we're seeing is many of the cloud providers are also adopting DT frameworks. So they're providing some level of I know that Azure and AWS both have hooks into being able to provide a DT framework, which obviously is provided you have good connectivity, you're still able to do relatively real-time, near real-time applications.
Mm-hmm. I know ISO is trying to establish a standard, international standard for digital twin. Do you see any de facto standard already being used in company? Because that's different data needed to be shared, and different protocol need to be used, communication and so on. If people use it in a different way, obviously it will create confusion for the user. Any de facto standard already exists?
No, unfortunately, there's no clear, not yet a standard, although I believe that's in the works by a few of the standards bodies. There's a lot of it is really is still in research mode. There's a few papers that I've read. I can point you to around DT, that was written in the last 2 to 3 years, both around what types of very specifically what types of algorithms to use for different, whether it's for a particular type of maintenance or whether it's a particular type of production process, or even in terms of forecasting or all of those things. So there exists a lot of literature and research out there that correlates different types of applications to different types of methodologies. I think that is a good start, but there does need to be more work done on the standardization as far as frameworks go. I think somebody asked a question here about, can we downsize it to smaller businesses? And absolutely, I think that is, for this to gain mass adoption, you really need to be able to scale down the DT framework so that you can apply it to smaller problems or a smaller scale environments.
Very good. So I'm also waiting for the questions from online participants. If you have any questions, suggestions, or comments, please share with us. In the meantime, we can continue the discussion between the two of us. Related to the utilization or application of a digital twin for companies, especially for SME companies, creating model, especially creating accurate model, is not that easy. They need to have the expertise, the skills in order to create them. That's one aspect. The other one is how to build and maintain digital thread for a company. This is another challenge. Do you have any idea or any thoughts to share with us? Or any software we can use?
Yeah, there is, I mentioned there's a variety of different tools and processes. I mean, although there's no clear standard, there are a variety of tools. I am happy to share that with you subsequently as well. But there are, just like you have frameworks for AI, you also have certain frameworks. I talked about AWS and Azure having certain frameworks for DT that help you to structure your design and process in a way that enable you to quickly, at least a lot of the compute and storage and all of those things are taken care of. The models, there are a few models available in terms of design. I'm happy to share a paper that I came across which talks specifically about applying different methodologies to different use cases. So again, it depends on whether you're applying it at the front end of the process or the back end of the process. There's variation in terms of how you would use not just the DT part, but also the AI part, the machine learning models that you have.
Yeah, I understand that model within DT is a highly domain-specific, application-specific. Suppose we can create an accurate model. However, the real world is dynamic. Over time, the model may drift away. How to keep the DT model up to the state of reality is that we can use a sensor to do the job, or we need to modify the model from time to time, especially in a dynamic fashion. Is this something we need to consider?
Yeah, one of the things we always look at is how there's always a redundancy built in, because if the sensors are faulty, for example, or they're for some reason providing wrong information, you need to be able to fall back to a default range that you have, right? So a lot of it comes down to how you define, I think upfront defining what the value ranges should be, what the standard deviation should be for different elements, for the different components, different variables. That's very critical. So a lot of work has to be done upfront. I mean, whoever asked the question is absolutely right, is that there's a significant amount of effort put in the creation of the DT itself that takes months, if not a few years to model and perfect it.
Mm-hmm. Yeah, and linking this digital twin to sustainability, which is one of the topics you covered today. If sustainability was like a CO2 emission is calculated in the digital twin by analytics, it's a sort of a model-based calculation or best guess estimation. And this compared with the measurement in reality, there may be some difference. How accurate the digital twin estimation is acceptable, let's say 95%, then we can rely on digital twin. Or for companies, they still need to use a measurement-based approach. So how to deal with this two type of approach in reality?
Well, I don't see them as different because the DT approach is also based on measurement. I mean, they are coming from sensors in real time, so it's not like you're manufacturing the data. What you're
I mean, here is a sustainability calculation. The sensor data is you can.
I know, but the sustainability,
like vibration, but not sustainability, right?
I know, but the sustainability data, whether you're looking at emissions, whether you're looking at wastage, you're looking at energy usage, all of those things are driven by the information you're getting from sensors, right? And even in today's world, if you look at how sustainability reporting is done, it's largely done by a finger in the air estimate. I mean, yes, you get reports from every one of your plants, your factories, your assets, but not all of it is automated today. So in many cases, it's done when done by a survey. Somebody sends out a survey, say, how much time did you spend going from this plant to that plant? As a result, how much fuel did you use? So those process, even today, it's very, very ad hoc, and it's not repeatable. It's not a repeatable process. I think with DT, you're actually be able to automate it to a large extent. I'd say, even if it's 80% accurate, you're better off than the current status. And then on top of that, you're able to repeat that process so that in real time, you're able to say, what is my current emission status, or what's my current energy status?
Yeah, that's true. Especially use the DT, we can look into the future based on the current sensor data, do some estimation. We know what is going to happen potentially in the future. That's also useful. I do not see further questions from our audience. I think pretty much the audience are convinced, they are clear about the discussion today. Before I wrap up today's webinar, I would like to thank you again. Thank you for sharing your wonderful keynote with us, and I also wanted to thank our online audience for listening and for participating in the discussion. The next AI for manufacturing webinar is scheduled on April 24 at 10 a.m. Central European Time. Professor George Huang of Hong Kong Polytechnic University will present another keynote on cyber-physical internet. In short, it's called CPI. Sending and receiving manufactured product, just like sending and receiving instant messages. This is another interesting topic. I hope all of you can participate. Please stay tuned. Have a great day, and bye for now.
Thanks.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
AI is a powerful tool.
This summit can help ensure that artificial intelligence charts a course that benefits humanity and bolsters our shared values.
Mm-hmm.